The Russians started talking about building their own 5G gear in 2016. Some members of the government pushed to back local enterprises to ensure full localization, while others suggested promoting collaboration with international companies. A few still simply wanted to ensure timely access to the best available equipment. Previous Russian 3G and 4G networks had relied heavily on European and later Chinese equipment. The factors driving Russia to develop its own 5G technology mirrors those of the United States and China, notably vast market potential, security concerns, and the desire for sovereignty. Following its invasion of Ukraine, Western sanctions blocked Russia's access to 5G equipment from vendors like Ericsson and Nokia. Besides that, they are afraid equipment from other countries could be turned off or used to spy on them in a time of conflict. They wanted technological sovereignty. The second group seemed to have won the debate initially. In 2021, Yadro, a Russian computer manufacturer, and Nokia entered into a memorandum of understanding to establish a joint venture aimed at producing 4G and 5G base stations in Russia. This agreement came after the government declared that, starting in 2023, there would be a ban on the import of base stations into the country. The Nokia deal gave Yadro 51% of the joint venture, with Nokia taking the remaining 49%. Nokia was to provide software, proprietary hardware, and the manufacturing know-how. Production was to be launched at the Yadro factory, which was being built in Dubna, a town located south of Moscow. Competitor Huawei had already set up several R&D centers in Russia and was already looking to localize their base stations. In June 2019, Huawei revealed that it was partnering with a local telecoms operator, MTS, to study 5G technologies and start pilot projects for mobile networks in Russia. That same year, Ericsson launched its 5G Innovation Center in Moscow, and by 2021, media reports indicated that the company was gearing up to localize the production of 5G base stations in Russia. They intended to collaborate with the GS Group at a facility located in the Russian enclave of Kaliningrad. The GS Group is a Kaliningrad-based manufacturer of diverse range of electronic products from semiconductor packaging to automotive parts. All these projects came to a standstill after sanctions were placed on Russia following its invasion of Ukraine in early 2022. Huawei, which had significant R&D activities in Russia, began to downsize its operations. Nokia and Ericsson quickly shut down operations and exited the market. Russian telecom operators had stockpiles of 4G base stations, so the abrupt departure of foreign companies did not significantly disrupt mobile services. Faced with the situation, the Russian government doubled down on the policy it had already earlier introduced in 2018 to assist local firms in manufacturing base stations. A consortium of state and private companies were organized under the leadership of Skoltech, a Russian research university and startup incubator modeled after MIT's D-Lab. Earlier in 2019, state-owned entities Rostec, the parent company of Sukhoi fighters, and Rostelecom, the government-controlled telecoms operator, became part of the consortium. In 2020, another group of private companies and top research institutes were selected to join the consortium, including Radio Gigabit, Eltex, Micron, and the Tom State University for Radio Electronics. The Russian base station market is ripe with opportunity, especially with the rise of 5G. 5G technology requires more base stations per square area, and Russia is very big. In the coming years, Russia would need between 40,000 to 60,000 base stations annually. And due to recent sanctions and the slowdowns in deliveries, some estimates suggest that this number is bigger, closer to 80,000 to 100,000 base stations required annually. And Russia is one of the few G20 countries without 5G mobile networks. It's dropped out of the top 100 countries with the fastest mobile internet, moving from 99th place to 102nd place in 2023. The first results of the Skoltech consortium is a new telecoms company called Irteya. Russian mobile operator MTS, the parent company of Irteya, was among the original members of the Skoltech consortium to create 5G Open RAN base stations. It took them 3 years to announce their developments. In 2021, they publicly tested their first prototype and later presented it at the St. Petersburg International Gas Forum a few months later. The Skoltech team developed the software and distributed units with hardware companies Eltex and Micron building the prototype radio module. The Skoltech group took about 39 months to develop the 5G software and hardware, with the Russian government footing about 70% of the development costs. After lab testing, they moved to pilot testing, installing 100 base stations for 5G in the Moscow metro and in companies within pilot areas in Moscow and St. Petersburg. Following that, MTS moved about 35 people from the Skoltech team to its newly established company, Irteya. Their goal was to finish development of the Skoltech base station and start small-scale production in 2024, increase production in 2025, and achieve full-scale output by 2026. Irteya was initially 100% owned by MTS, but in 2024, MTS sold 50% stake in the company to Aquarius, a Russian computer and server manufacturer. So while Micron and Eltex worked on the Skoltech prototypes, Aquarius is now in charge of manufacturing the final product. The prototype Skoltech units used AMD's Zinc ultra-scale accelerators for the base station. The AMD chip manages beam forming needed to shape and steer beams for multiple users simultaneously in real time. This requires enormous computational power with low deterministic latency. The production version of the Irteya unit probably uses the same accelerators or units from either Huawei or other Chinese manufacturers. Irteya develops their own transceiver, which utilizes gallium nitride transistors from Russian semiconductor company Melandra. A transceiver combines both a transmitter and a receiver in a single unit. It is usually made of radio frequency filters, digital signal processors, amplifiers, and digital to analog converters. In 2025, Irteya and the Russian semiconductor maker Micron signed agreement to supply 10 types of microcircuits for base stations. The contract was for chips to control power supply, control antennas, and a microcontroller to launch the digital module of the base station. Micron produces a RISC-V microcontroller called the Amor. Micron's parent company, the Element Group, with the help of MIPT Telecom, has launched the production of radio frequency amplifier modules and power supplies used for base stations. MIPT Telecom has also developed a MIMO antenna. The sector antenna operates in the N79 frequency band from 4800 MHz to 5000 MHz, with data transfer speeds reaching 1 gigabits per second. The Irteya setup is versatile. It supports single RAN tech, which means it supports 2G, 4G, and 5G networks at the same time. For telecoms operators, universal base stations cut down on equipment costs. They may have higher upfront price, but they eventually save money by eliminating the cost associated with maintaining separate networks for each standard. Plus, it reduces the need for new sites and simplifies network management. In 2023, Irteya entered into a forward contract with MTS to provide them with 20,000 base stations. By 2024, pilot installations began in cities like St. Petersburg, Kazan, Novosibirsk, and Nizhny Novgorod, along with the Moscow and Leningrad regions. Irteya also started testing of its 5G equipment in Belarus in the summer of 2025. After parting ways with Nokia, Yadro pushed forward with its ambitions to become a key player in the telecoms equipment market. Established in 2014, this Russian company manufactures a range of tech products like computers, servers, switches, laptops, tablets, and software. They carved out a niche, quickly becoming a leading supplier of server and storage solutions for data centers throughout Russia. Yadro's youthful team collaborates with Russian universities to innovate and attract new talents. In 2023, they joined forces with Siberian State University of Telecoms and Informatics to develop systems for the next generation of 5G and 6G base stations. They launched a joint engineering center in Novosibirsk equipped with labs dedicated to creating and testing telecoms equipment. With more than 1,500 engineers across 3 R&D centers in Moscow, St. Petersburg, and Nizhny Novgorod, Yadro is planning to take a big slice of the Russian telecoms market. Their hardware initially supports only 2G and 4G standards, but with expansion cards and software updates, it will eventually support 5G also. Companies like Nokia have through the years developed comprehensive solutions for 2G, 4G, and 5G. Their code base is massive, millions of lines written by thousands of engineers over many years. This code manages network expansion without disrupting ongoing services, optimizes resources during slower times, and allows for updates and new features while still running. The majority of Yadro's team focuses on this software stack, working on features for 2G, 4G, and 5G, which consists of around 17 million lines of code. To put this into perspective, the YouTube site is roughly 5 million lines of code. Telecom base stations are increasingly being designed as software-defined systems. This approach allows for greater flexibility, scalability, and ability to adapt to new technologies and standards. Software-defined base stations enable telecoms operators to easily upgrade and integrate various wireless generations without the need for physical hardware changes. 5G technology is a prime example where base stations are designed to be reprogrammable and can support multiple generations, enhancing interoperability, reducing costs, and allowing for open-source solutions as alternatives to traditional base stations. These advancements reflect a significant shift towards more efficient and adaptable communications infrastructure in the telecom sector. An Open RAN base station is made up of 3 units: the radio unit, the distributed unit, and the centralized unit. The software in the distributed unit handles very fast and time-sensitive jobs needed to control the radio signals sent and received by the antennas. The distributed unit is located right next to the antennas to take care of the basic tasks of how radio signals are handled. This includes things like modulation and demodulation for converting data into radio waves and back again, for error correction, for adding extra data to fix errors, and beamforming for directing the radio signals towards mobile phones. It also handles important jobs like scheduling for quickly deciding which devices get to use a radio signal, and hard queue management for managing requests to resend data if some gets lost along the way. In contrast, the software within the centralized unit, typically deployed further from the cell site, is split into control plane and user plane components. The control plane manages important setup for your phone's connection. It's important for things like starting or ending your connection, handling handovers when you are on the move between cell areas, keeping the connection secure, and managing basic control information for your data. The user plane focuses on actual information you send and receive, like voice, web pages, or videos. It secures this data by encryption and decryption, makes the data packets smaller for efficiency via header compression, and makes sure important data gets priority through QoS enforcement and mapping. The software core domain handles a range of essential functions in the mobile network, like mobile mobility management, authentication, subscriber data management, and policy management. These are for managing your phone's connection as your phone switches from one station to another as you move around, checking who you are and what you're allowed to do, keeping track of your account details, and controlling network rules like speed limits and data priorities. Information about the semiconductors for the Yadro base station isn't readily available. Yadro owns Centercore, a chip design company that specializes in designing RISC-V chips. Their engineers are working on creating powerful server CPUs and FPGA chips. If they pull this off, they will stand alongside Huawei as one of the few companies designing their own chips for base stations. But in the meantime, their equipment will most likely use CPUs from American giants Intel or AMD. In a big move, ICS Holding, Yadro's parent company, bought Micron, a leader in radio antennas and semiconductors, in 2025. Micron has been heavily involved in 5G development since 2020, particularly with Open RAN 5G transceivers and MIMO antennas. They played a leading role in the Skoltech MTS 5G project, contributing to the creation of the Irteya base stations. With this acquisition, Yadro will most likely source most of its antenna and radio unit components from Micron. In 2023, Yadro began lab testing their system. By 2024, they advanced to field tests with major operators like Megaphone, Beeline, and Tele2. These tests focused on radio modules and server stacks. Back in 2022, Yadro secured contracts to deliver 55,000 base stations to these companies by 2030. Besides lab work, pilot tests for Yadro's base stations are happening in two small towns in the Leningrad region. Fast forward to 2025, Yadro and Beeline showcased the Yadro BTS 8100 base stations at the Digital Industry Conference of Russia trade show. This base station is built on the 5G-ready hardware platform capable of supporting all necessary frequency bands 800, 900, 1800, 2100, 2300, and 2600 MHz. Production of the base station started in early 2025 at Yadro's Dubna factory, which was established for computer equipment production back in 2023, and they aim to achieve full production capacity by December 2028. Russia represents the world's fifth largest market for base stations deployments, a ranking driven by its vast geographical expanse and large population. This extensive infrastructure supports one of the top 10 highest numbers of subscribed devices globally. However, the country's scale in terms of hardware and subscribers does not translate directly into proportional revenue. Russian telecom operators cannot command the same profit margins as their European or American counterparts. Consequently, despite serving a population that rivals or exceeds major Western nations, the industry's overall revenue is only comparable to that of large European countries with roughly half the population, namely France, the UK, and Germany. The latest antenna technology for mobile telecoms is called MIMO, multiple out, multiple in antennas. 5G signals at high frequencies have very high path loss and are easily blocked. To overcome this, you need massive MIMO antennas with hundreds of elements to provide enough beamforming power to make a reliable connection. An 8 transmit 8 receive array would be completely ineffective at millimeter wave frequencies where 5G thrives. MIMO allows a base station to talk to multiple devices simultaneously on the same frequency resource. An 8 transmit 8 receive antenna array can serve far fewer users simultaneously than a 64 transmit 64 receive array. The most advanced 4G network maxed out at 4 transmit 4 receive MIMOs for mobile devices and 8 transmit 8 receive MIMOs for base stations. 8T8R MIMOs was the theoretical peak for 4G, defined by the 3GPP standards. 8T8R and even 4G 4R MIMOs are also used in 5G, particularly in low-frequency bands. But that's just the starting point. 5G's true potential is unlocked with much larger antenna arrays, which is why vendors quickly moved to 32T32R and 64T64R MIMO antennas. A 64-element array can form highly precise narrow beams. This means energy is focused directly on the user's device and the beams to different users can be spatially separated, minimizing interference between them. This dramatically improves overall network spectral efficiency. A 64T64R massive MIMO base station can serve dozens of users simultaneously on the same time frequency resource. This is a massive leap in capacity over 4G systems and is essential for meeting the skyrocketing data demands. Deploying larger antenna arrays isn't free and involves several critical trade-offs. Each antenna element requires its own radio frequency chain, power amplifier, low noise amplifier, mixers, filters, and analog to digital converters. 64 elements means 64 complete radio frequency chains, which is expensive and power hungry. The computational complexity of calculating the optimal beamforming weights and processing signals from dozens of users simultaneously is enormous. It requires powerful specialized FPGA or ASIC processors and advanced algorithms, leading to higher costs and power consumption. The 64T64R massive MIMO antenna panel is overkill for a rural area with few users, but necessary for urban areas like large cities. It provides the most value in dense urban environments, stadiums, and traffic hotspots where its capacity and multiplexing advantages are fully utilized. For other scenarios, smaller 8T, 8R, or 32T, 32R configurations might be more economical. The sanctions on Russian semiconductor industry has forced their scientists to come up with some interesting solutions for massive MIMO antennas and their beamforming systems. Researchers at the Moscow Institute of Physics and Technology have developed a novel 5G MIMO antenna for local base stations, showcasing a significant departure from conventional flat panel designs. The key innovation lies in the complex three-dimensional geometry of each antenna emitter. Current antenna arrays are usually flat, thereby complicating the search for ideal geometry. Unlike traditional flat arrays, MIPT's design explores the third dimension to achieve exceptional performance, including more than 25 decibels of isolation between adjacent elements, minimizing interference, highly directive radiation patterns for more efficient signal transmission, and gain over 11.3 dB across the wide bandwidth from 2.5 to 4.5 GHz. To create this optimal shape, MIPT employed a sophisticated two-step process using bio-inspired algorithms. They use genetic topology optimization to find an optimum antenna structure and particle swarm algorithms, an algorithm that mimics a swarm of insects to fine-tune the design for maximum bandwidth and gain. A major challenge was manufacturing, as the antenna dimensions required precision for hundreds of a millimeter. MIPT ingeniously bypassed expensive metal 3D printing by developing a hybrid process which involved using fused deposition modeling 3D printing and electroplating. They first 3D print a photopolymer mold of the antenna, then apply an electromechanical metal coating to the mold, and then remove the polymer substrate with heat, leaving behind a pure intricate metal structure. This approach allows for 3D antenna emitter designs that are impossible with standard PCB-based flat antennas. The result is a component with approximately twice the overall performance of competing MIMO antennas, achieving higher efficiency through constructive interference with its complex 3D structure. St. Petersburg Electrotechnical University (LETI) is developing a specialized microwave antenna for 5G that dynamically focuses signals towards dense user areas, effectively countering the high path loss of millimeter wave propagation. Typically, 5G communication standard includes two frequency bands, FR1 at 0.6 to 6 GHz and FR2 at 24 to 52 GHz. 5G's use of high-frequency millimeter wave presents a physical challenge. These signals attenuate rapidly, severely limiting each base station's coverage area and necessitating an increase in number of expensive cell sites per square area. Instead of broadcasting wide, weak signals, the solution is to use antennas that can form multiple highly focused beams. In current systems, you need one expensive transceiver for every antenna element. LETI's hybrid approach centralizes the complex and expensive active electronics, like power amplifiers, into a multi-channel transceiver that then feeds into a tunable reflective phase antenna array, shaping and focusing the incoming waves into a highly directional beam that can pass through it. This system integrates three core components: an irradiator, a focusing lens, and a tunable reflective phase array of 100 elements to achieve high directivity and electronic space scanning. Precision beam steering is accomplished not through complex phase shifters, but with semiconductor diodes embedded in the array. These diodes are controlled by a dedicated system using high-precision 12-bit digital-to-analog converters, which apply specific voltages to instantly alter each diode's electrical state. This allows for real-time optimization of the radiation pattern, maximizing signal strength towards users and minimizing wasted energy from internal reflections. By combining the signals from many small elements coherently, you can create a powerful focused beam towards the user. This extends range and improves signal quality. More elements means more powerful and focused beams. It also allows you to pinpoint users more accurately, which dramatically reduces interference between users. Ericsson and Nokia produce 64T64R and 32T32R, which have 128 and 68 radiating elements respectively, each antenna having 2 frequency radiators. If this prototype has 100 non-polarized elements, then this will fall between 64 and 32 in terms of beamforming capabilities. High antenna element configuration provides the highest beamforming gain, making it ideal for areas requiring the best possible coverage with the highest data rates. In contrast, the number of transceiver chains is what determines the number of users a unit can serve at an exact time on the same frequency. Each transmit-receive chain is an independent radio channel that can transmit and receive a unique data stream. A 100 antenna system can have 10, 20, or even 50 transmit and 100 receive chains. However, without an official specification from Leti, you cannot be certain. Breaking the link between the number of antennas and the number of transceivers also provides more flexibility because you can better match the number of transceiver and antennas depending on the projected load of a specific cell site location. Compared to the current fully digital solutions, it is more energy efficient and has lower cost because you can use fewer expensive digital transceiver chains. For example, instead of 100 transceivers for 100 antenna elements, you might use 16 transceivers, which will then feed an analog network connected to the 100 elements. The key operational benefit of this design is the significant reduction in computational load for the system's baseband accelerators. Handling the complex stacks of physical beamforming internally, the antenna offloads approximately 30 to 50% of beam-related processing. This frees up accelerator resources like FPGAs or DSPs to focus on critical higher-layer functions like channel coding, modulation, encryption, and advanced inference management. This will be very relevant to the Russians because it will help them build competitive radio units without access to the most powerful FPGA and ASIC chips in the world. According to Leti, this antenna is also cheaper to manufacture with stainless steel components fabricated by laser cutting and 3D printed plastic housing. Other Russian MIMO antenna manufacturers are Antex, Micron, and the Ivesh radio plant. The Ishvek radio plant currently makes 8T8R MIMOs, Antex is at 16T16R, and Micron is aiming for 32T32R. Without the sanctions, Russia was never positioned to succeed in building its own base stations. The country faced fundamental structural disadvantages that would have made any commercial entry into the global market virtually impossible. Its companies lacked access to the strong capital markets that benefit American firms. There was no venture capital ecosystem, no cheap debt through low-interest loans, and no patient equity funding to sustain years of unprofitable development. They lacked the deep knowledge and accumulated experience of base station design necessary to build a superior product that might have convinced prospective customers to overlook concerns about trust, service, and reliability. They lacked the sophisticated supply chains that enable Vietnam and China to produce considerably cheaper equipment, the kind of cost advantage that might have persuaded buyers to accept compromises on brand reputation, security certification, or interoperability. They lacked the brand heritage and trusted relationships that European vendors have cultivated over decades, which could have compensated for new entrants' disadvantages. And crucially, they lacked a protected domestic market of sufficient scale, nothing comparable to China or India, and didn't have an environment where local operators would patiently deploy untested gear, help hone the product through real-world feedback, and generate economies of scale needed to drive down unit costs while eliminating teething problems. The sanctions fundamentally altered this equation. By cutting Russia off from European suppliers and pressuring Chinese vendors to limit engagement, they created an artificial but urgent market opportunity that did not previously exist. Russian operators, facing the prospect of being unable to maintain their networks, had no choice but to support domestic development. Critically, this market creation was paired with sustained government backing for research and development through startup incubators like Skoltech, universities such as MIPT and LETI, and scientific institutions including NII Radio. This ecosystem provided a technical foundation that private capital could not. And perhaps most importantly, the mobile operators themselves, MTS, T2, Megaphone, and Telecom, became direct participants in the development of the process, investing in manufacturers, placing early orders, and providing real-world deployment feedback that is essential to maturing any telecoms product. This combination of forced market demand, state-funded research, and operator-led development is what enabled Russia to succeed where, absent the sanctions, it would certainly have failed. So that's it for the first half of this video. The second half will be next. Stay tuned.